Hi everyone. So first I would like to thank the organizers for giving me an opportunity to speak in front of this audience. So I'll be mainly speaking about novel triggers in CMS, opening new doors to uncharted territories. This is the first part of the talk, and at the very end I have 2 slides about a work where I collaborated with Rohini. So many of us are very familiar with the CMS experiment. It is one of the general purpose experiment in the Large Hadron Collider Accelerator Complex. Now, this term trigger may seem like a jargon unless you work in this area of experimental high energy physics. So what is a trigger and why it is so important for Hadron Collider experiments? So actually a collider produces an incredible amount of data. Just to give some numbers, in 1 second LHC produces 33 times 10 to the power 6 proton-proton collisions. That is an incredible number of events which the experiments cannot save in the disk. So for example, CMS, one of the biggest general purpose experiment, can accept and store only 10 to the power 3 proton-proton collisions per second, which means that about 99.9% of the collisions that LHC is giving us, we have to discard them in real time. And which events to discard and which events to keep, this very important decision-making step is called trigger. So for each proton-proton collision, either the trigger decides yes, keep that event, or it decides no, then that event will be lost forever. So what I'm trying to point out here is that the triggering step is ultimate and irreversible. So if we make a mistake there, there is no way that we can rectify that mistake. So, proton-proton collisions at LHC, as I just mentioned, is happening at an incredibly high rate, and we have this 2-level trigger system. The level 1, which is implemented in hardware, this reduces this rate of 33 megahertz to 110 kilohertz approximately, and then there is a software-based trigger called high-level trigger that reduces this rate further. Mainly to 2 kilohertz, this is the standard mode, and then we have some special modes called parking and scouting, and I'll speak more about those later on. And in high luminosity LHC, these numbers are going to change, but I will not discuss those. And all the details of these trigger systems, both level 1 and HLT, they are documented in these publications, and this is coming up in physics reports. So finally, this is the amount of data that CMS finally collects and is available to do physics analysis. CMS has a very broad physics program. These 2 plots, they are both dimuon invariant mass plot. In the left one, you are seeing that the highest event that we see in data in black points, that is appearing around 3 TeV. So this is a TeV scale plot. Whereas in this plot, in the right-hand side, this is also dimuon invariant mass, but this is spanning this sub-GeV scale. So from TeV scale to sub-GeV scale, CMS can look into this entire spectrum, which is amazing. So there are different kinds of physics analysis in CMS. Some focus on direct search for BSM particles. Then there are precision measurements in the electroweak top or Higgs sector. There are dedicated programs for B physics and heavy ion. Just to give some examples, CMS has just published a paper focusing on this signature where LHC has been used as a photon collider, and this one, for example, where LHC is used as a boson collider. And this broad physics program is also reflected by the amount of published paper that we have so far from CMS collaboration. Now, we need to appreciate one fact that behind every successful physics analysis in CMS, there is a trigger, which means that CMS also have a very broad trigger program, and in this talk, I will try to give a glimpse of it. This is obviously not exhaustive. This is mostly personal choice. So where is the novelty in CMS triggers? The novelty is everywhere. It's there in the trigger strategies, parking and scouting, which I just pointed out, but I will elaborate in a moment. Then there is novelty in the variety of signatures. For example, we look for very challenging long-lived signatures and very low PT signatures, jet substructure, and so on. Then there is novelty in the way we use machine learning, both supervised and unsupervised, already in the trigger level. And then also we use GPU, but I will not speak about this part because of time restriction. So I will start with the trigger strategy, namely parking and scouting. So one raw event in CMS is on average 1 MB, which is huge. So in principle, there was no problem in relaxing the trigger threshold and taking more data, but we cannot easily do that because the amount of data that will be huge and we will not be able to save all those events. So a simple way out is that we can save the objects that are already reconstructed at HLT and we can perform physics analysis with them. But HLT or high level trigger, this is a real-time reconstruction, and we often think that real-time reconstruction may not be as good as offline reconstruction, but that is not the case anymore. As you can see here, this is jet energy resolution as a function of PT, transverse momentum, and you see that the resolution in scouting, which is the HLT level reconstruction, and offline reconstruction, they are basically very similar. So using scouting at HLT, we have performed many analyses. This is just one example, and this is search for dark photon in dimuon channel, and this is just the prompt decay of dark photon, which means dark photon is not long-lived in this case. And so we published 2 papers focusing on 2 different mass ranges. This one starts from 11 GeV and goes up to 200 GeV, but scouting triggers are used from 11 to 45 GeV mass range. Whereas in this other paper, here the entire range, which is very, very low mass, so from 8 GeV and lesser than that, this is entirely based on scouting triggers. So probing this very low mass region was basically possible due to scouting. So then moving on to the parking strategy. So this is a little bit different than scouting, although this is also aiming towards the low PT signatures, but this is more like opportunistic or delayed offline reconstruction. So in this case, we are not using the HLT level reconstruction, we are reconstructing them offline, but it is possible that we will not be able to do that offline reconstruction immediately, and we will do it when our computing resources are free. Other than that, parking and the standard triggers are basically the same. So using the data collected by parking triggers, there were again many analyses that are available. This is just one example. This is search for rare decay, D0 going to dimuon, and this analysis gives the most stringent limit till date, which is still far away from the standard model prediction, but this is the best we have so far. Now moving on to novelty in variety of signatures, I will only speak about long-lived and displaced particles. So this is the cross-section of CMS, just one slice of it, where you can see that the proton-proton collision happened here, and then we have a tracker, electromagnetic calorimeter to detect electrons and photons, then hadronic calorimeter for detecting hadrons. Then we have the magnet system to bend the tracks here in tracker, and then finally we have the muon system to detect the muons. Now, for long-lived particles, we know that this is becoming very popular lately, but if we think about old days when LHC was just starting, most of our analysis used to focus on prompt decay of any BSM particle, or it used to focus on those cases where BSM is stable and it will be produced and then it will just go out of the detector undetected, which will give rise to a significant amount of missing transverse energy. So these two regions of the mass decay length plane was focused on, and there was this entire area which was, people did not do too many analysis in focusing on this area. So now that BSM is not discovered here and there so far, people are becoming more and more interested in long-lived signatures, which can arise in a BSM model due to various reasons, for example, suppression from heavy propagator or small coupling and so on. So depending on, so after a long-lived particle is produced in LHC, it will, since it's long-lived, it will move some distance before decaying, and depending on where the long-lived particle decays, the signature in CMS will be strikingly different. For example, if a long-lived particle decays inside the tracker, and let's assume that it is always decaying to jets or spray of hadrons, in this case you will get a displaced vortex and you will get displaced jets. On the other hand, if the LLP decays just at the end of the tracker and before ECAL, you will get trackless jets. Then if it decays before HCAL, after ECAL, then you will get jets which neither have matching tracks and nor have any electromagnetic energy deposit, which is a very weird kind of jet. And in this extreme scenario where the LLP is decaying after the solenoid, so in the muon system, you will just get a lot of hits which you can cluster in the muon system. So jets in muon system is something we were not studying 10 years ago, but we are studying this now. Okay, so all these signatures are being studied, and most of them have published paper. I'm just showing one example where you have a standard model Higgs decaying to two long-lived scalars, which then decays to jets. So there is two dijet systems, and this analysis was published, and it gives the best limit still dead, which was possible due to dedicated high-level trigger and smart use of machine learning in the offline analysis. So then I will move on to the next one, which is how we are using machine learning already in the trigger level. So if you have a signature in mind, we obviously can write a trigger for it. If you do not have a signature in mind, we have a trigger for that too. So if you are thinking how, let me explain. So we know that beyond standard model has to exist, we just don't know how it will show up in our detector. So what we have done is that we have trained a variational autoencoder which will learn typical standard model signatures at LHC, and then we let it pick those data events that do not look typical, so atypical events that the variational autoencoder sees in the data, and we search for BSM in those atypical events. So this is one such event that was selected by our anomaly detection trigger. We have two of them. These are just names which are not so important, but this is an event that was flagged as atypical event by one of those triggers, and it has a lot of energy deposits, and we have a bulk of these events, many of them, and an analysis is going on to understand what these events are. So at the very beginning of my talk, I mentioned that 99.9% of PP collisions are discarded in real time. I'm sure this is bugging some of you. What if BSM is hidden in this 99.9%? How long do I have, Shilpi? Okay, perfect. So we have also thought about it, thought about this case because this was bugging us as well. So what we are going to do in the high luminosity LHC is that this 33 megahertz that is coming from LHC, we are going to scout all of them before taking the level 1 trigger decision. And this 33 megahertz of data, this will be saved offline, and will be available for physics analysis. The only caveat is that this reconstruction will be level 1 level reconstruction. So it is even worse than HLT level reconstruction, and we will see how it affects our analysis. For example, if you are doing just a bump hunt kind of thing, it should not affect too much. Already a demonstrator of this level 1 scouting is running in run 3, and this is running as a proof of concept because we have to prove that something like this is possible to do computing wise. So that is why this is already running. Although the level 1 system now and the level 1 system in HLLHC is very, very different. So you can see that this is a Daimion invariant mass for Monte Carlo and data, and that do not match very well because this system is still a work in progress and doesn't work very well so far. So we have to improve this before HLLHC starts. So I'm coming to an end to the first part of my talk. So the first phase of LHC program will be completed next year. We have taken a whole lot of data, 24 femtobarn inverse in run 1, 137 in run 2, 170 so far in run 3. We are currently working on upgrading the detector and the trigger system for high luminosity LHC, and the target is to collect 3000 femtobarn inverse by 2041. Meanwhile, we are pushing the detector beyond its limits. We are collecting data at trigger level at 7 kilohertz, as I mentioned in the beginning, which is 70% already of HLLHC, and 7 times the run 2 nominal operations. We are in run 3 now. And we are recording up to 63 simultaneous collisions per event, also known as pile-up, which is 2.5 times CMS design and already 45% of HLLHC. So it is fair to say that the future is now. Now I'll move on to the next part. I just have 2 slides about this paper. I will not discuss the physics of this paper. I just wanted to mention that I had this opportunity to work with Rohini in the context of this HEP phenomenology paper. This is about novel signature for long-lived particles at the LHC. So you see that what I just discussed in the talk and this paper, the content of this paper was very, very related. I still work on similar things in CMS. And so the other collaborators are also present in the audience. So Shankho, Genevieve, Biplab, Fauzi, so they are all present in the audience. So here we talked about decay of very high mass long-lived particles where a fraction of the decay products can move backwards. So we will see a very striking signature of backward moving objects in our detectors, which we generally do not try to reconstruct. So that was the idea. And the authors of these papers have given talks at many platforms about this paper. This is my talk in CERN in the LHC long-lived particle workshop in May 2018. It was still before this paper was published. And this is Rohini giving talk on the same paper in NICHEF Theory Meets Experiment workshop in the same year in October. That's all I have to say. Thank you.